So thank you, and thank you everyone for attending. You guys make it all worthwhile. You'll see, obviously from the date on this, that this presentation is a couple of years old now, but I think it's still useful. What I want you guys to take away from this is the approach we take to looking at platform level changes when we're either building out new database platforms in-house or when we're forced into making some changes, which this was a case example of. So hopefully, first a little bit about me. Probably the easiest way to find out about me, because I have a relatively rare name, is to Google me. And you probably get results in the order in which you could most helpfully engage with me. So you might find me on Twitter. That will be a combination of posts about Oracle and databases, but it also contains quite a lot of UK politics, a fair amount of cricket, and a fair amount of teasing people that I know. So it's not a purely technical forum. I'm a member of the Oak Table. You can reach out to me on LinkedIn, and I've contributed to a couple of books over time. The next slide, I don't normally do, but it helps set the context for what happened, you know, what prompted this presentation. So I work for a company called the IHS Markit, and this is our look how big we are slide. We have a very large customer base, and we supply data of various types to all these people here. So if you've heard of a large corporate, we probably supply data to them. If you've heard of an energy company or you work for them, we supply data to you and analysis. We're pretty big in the financial markets world, and we're pretty much entirely a data, information and analytics company. So we have a lot of databases. So what I'm going to cover today is what the Spectre and Meltdown vulnerabilities were and what mitigations were available to us. And then a little bit about what happens when a story hits the press, which this one did. But mostly I want to cover how we test platform level changes, what results we drew from our testing for Spectre and Meltdown, and some lessons learned, and a little bit about validation might be in there, but it's not really relevant 2 years down the line. So first of all, the vulnerabilities. So there were three distinct vulnerabilities announced at almost exactly the same time. Two that were named Spectre, and one that was named Meltdown. And these were all a brand new class of attack against IT systems, about computer systems. So the first Spectre vulnerability is a bounds check vulnerability, which I'll cover in a bit. The second is about CPU target prediction or misprediction. And the Meltdown vulnerability is a method of accessing the memory space of a computer at a very high level. If you want to read in great detail, there's a spectreattack.com website, and there's a similar meltdownattack.com, and they contain the academic style papers that cover these vulnerabilities. So the first vulnerability is a bounds check bypass. So the description, and a happy little ghost with a branch in his hand. gives us a lot of words that DBAs probably won't be necessarily familiar with. So systems with microprocessors utilizing speculative execution and branch prediction may allow unauthorized disclosure of information to an attacker with local user access via a side channel analysis. Now, that's probably fairly meaningless to you, but systems with microprocessors that use speculative execution and branch prediction are all modern computers, all modern smartphones, pretty much you name it. It's a very old performance enhancement technique that chip manufacturers use. And the key thing in bold, if you have local user access, then you can construct malicious code that can leak data that you shouldn't be able to read. So a bounds check works like this. So this is good code, okay? So the idea is that we have a program that executes a check here in line 1, make sure that my variable x is less than the appropriate size that I've allowed that array variable to be. If it is, then assign a value to another variable. So that's actually good practice to check that you're not overflowing the size of your arrays. That's what's going on here. However, if you write a program that contains code like this and repeatedly run it, the CPU will learn that generally that bounds check is true. Then when you execute it where the bounds check is not true, the CPU will nevertheless speculatively execute the code that it would expect generally to run, and it will read that data into the cache. The location that is read into the cache will be dependent on the value of x. And then when the if condition, when the is the x less than the array size condition is checked, that cache is not emptied. So data that you should never have accessed has been loaded into the cache of your program. And that's a vulnerability. Branch target injection. So this is the part of a microprocessor that predicts what conditional paths the code will take. And the idea here is you take some common code. So the example attack uses NTDLL, which is a very common shared library on Windows systems. And obviously sleep is a very common function. You then cause it to be executed several times, again training the CPUs as to what to expect, and then load the sorry, I've clicked too quickly. You then mistrain the CPU with this one so that you're loading the wrong part of memory into the local program space. That's branch target injection. And Meltdown, slightly different graphic here. As we all probably know, in modern virtual memory architectures, the application memory is isolated. And kernel memory is isolated from the applications. And that's controlled by a security bit that is set when you enter or when you leave kernel mode. So usually a system interrupt. What this means is that every process will have some kernel memory mapped into its address space. Purely so that processes can do things like issue requests for IO, for example. and other interrupts. IO is obviously the example I'm going to be looking at today. Speculative execution doesn't check the bit before it carries out the speculative execution. So it really, this is doing some work that you think you may need to do in a little while. So you don't check whether you need to be able to read the data until the speculation either comes true or doesn't come true. And again, data is left in cache. This is kind of a function of how caches work. And the side channel analysis, which is a little bit of complexity, is a way of reading that memory from the cache. Now, the key thing here is that you can, if you maliciously construct your requests, go through the entire memory space of the machine and load it all into the program cache and leak that. So that's the Meltdown vulnerability. So what does this look like on a computer? This is from the disclosure, a whole set of obviously made up usernames and passwords. The Meltdown vulnerability reads all of that memory into file, and you'll see various of those passwords and websites and so on are contained in clear text in the memory dump, just as they were in the screenshot. So because you're able to access all of the program area on that machine, you can read any data from any process, and that's why Meltdown was such a big deal. So, in summary, Meltdown applies to everything, and it compromises all memory in the machine, which is clearly a very, very big deal. And it's mitigated by some KPTI patches. We'll come on to what that means in a minute, because there's a nice story about that. Spectre, those vulnerabilities require knowledge of the target software environment, and they require you to write code. So there's a distinct jump up in the level of difficulty to exploit the Spectre vulnerabilities. Variant 2, at the time I wrote this, was not mitigated by any OS patches and required hardware or at least microcode updates from the processor vendors. All of these, you need access to the target machine because you need to execute them in the on the machine where the memory that you're going to read is. There are patches available, KPTI, as I say, and some of these patches were shipped with the ability to disable them. And that was one of the things we wanted to look at. The various microcode patches, they came out in a not entirely confidence-inducing manner because they tended to be released by the processor vendor, then removed and replaced by a different version, and they settled down after about 2 or 3 months. And now all modern software compilers, this is a Visual Studio C compiler that I'm showing you an output from, will do Spectre checks for you. And obviously that's a recommendation. If you're doing software development, make sure you're using the latest toolset. Just a side note, because I like this, why are these patches called KPTI? Well, this is an extract from the Linux kernel developers mailing list. And you'll see that software developers, when asked to fix problems introduced by hardware people, don't necessarily view this with unmitigated joy. So that's where kernel page table isolation came from. The Linux kernel developers really had a bit of a hissy fit at the fact that the hardware that they relied on was also vulnerable. Anyway, I thought that might amuse at least a few of you. So I first became aware of all of this through industry press, like the Register. I think it's worth any IT professional keeping up with a few good industry feeds. The Register is a UK-based site, and I'm obviously in the UK. One of the things right from early on was there was a suggestion that fixing this problem would compromise the performance of the hardware. And as a database guy, database performance is an important concern for me. And it kind of made it onto geekier websites. So this was Reddit. If you have children who are teenagers, you'll know all about Reddit. But then what happened was this. Papers like the Financial Times and China Daily and the Washington Post and the New York Times started covering it, and started covering it on their front pages. And when that happens, this sort of thing happens. So we got an email company-wide from our CTO that said, look, you may be aware of this. These wonderful IT people are going to do something about it. It's the blanked out bit of that email. Those wonderful IT people, of whom I was one, the first they knew about it was when the corporate communication went round. So you might well ask the question, why should we test? We're probably going to have to apply these patches. You know, the impact is what it is. Well, round about the time we were looking at this, the estimates as to what difference it might make range from 2% through to 30%. And slightly worryingly, the 30% performance impact was based on a database, a relational database test. Now, losing a third of your performance of your system overnight doesn't seem like a very good idea. So, you know, we started asking ourselves questions like this. If our SLA-driven processes suddenly take 3 times as long or twice as long, what's the risk of this vulnerability to us? Similarly, you know, if it's just a small impact, if it's only 1 minute out of 10, probably we can live with that. But it would be good to know which it was. And in particular, because local access was required for these vulnerabilities to be exploited, in the case of database servers, there's a pretty strong argument that you only let people have access to those database servers that you actually trust in the first place. So end users' machines, including DBA's desktops, all were going to get the patches straight away because you don't want to leak the memory of, for example, somebody's SQL Plus session or somebody's SQL developer session. But our question here was, do we apply these patches or not to the database servers within IHS Market? You know, basically, the better you understand the impact of the problem, the better the decision that you can take. And particularly in this case, there were feature flags that could enable us to apply or not apply all of the fixes. So we could install the software fixes, but not enable them was the idea, if required. So when we're assessing new platforms, we do a whole bunch of tests, including some application specific tests for our applications. But we do some platform level tests, and we do some platform level performance tests. And you guys can do this as well. So as a standard, when we're on a platform, we will do something we call the logical I/O test from Kevin Clausen's SLOB benchmark. And that's a CPU performance measure. Often it's very common to see 99.7 or higher % of the database time during this test on CPU. Its PAL is the physical I/O test, and as its name suggests, this measures the performance of an I/O intensive workload. Both of those are very abstract tests. They are Oracle I/O tests, but they're not application-like tests. So we also run a Swingbench stress test. So that measures the impact on transactions per second and response times for a OLTP-like application. It's an order processing application, and gives us an idea of, well, yes, the platform looks as if it's, say, 20% better. What does that translate into in a sample realistic application? And at the time I wrote this, we didn't use the calling circle benchmark or the TPC-DS benchmark that's now in Swingbench, because we didn't have very many data warehouse type workloads characterized by large fact tables, populating materialized views and so on. Since I wrote this presentation, we have got a few critical data warehouse type workloads, and that's an area of ongoing research for us. And we use these tests to validate changes at the platform level. So if we're buying a new model of server, if we're deciding which type of CPU to put in a set of servers, because often that is available to you. If we're moving from Oracle 19 to Oracle 20, we will do this sort of test. When we made significant changes to our platforms, for example, when we introduced instance caging, we took a look at that. And both of these utilities are freely available and they're well documented. So those are the links at the bottom there. SLOB itself has got a very careful schema. I use this word schema in quotes because it's one table really. And there's the definition. The point of the minimized records per block is so that pretty much every database request in the SLOB workload results in a single block IO, or a number of single block IOs. So that's the entire schema. There is an update. Again, you're updating the beginning and end values within a block, within the sample data. That's what SLOB looks like. And there's only one query. It's a very simple query. You can see again, that's going to be an indexed query, looking up single blocks at a time. So the characteristics of SLOB, there is no contention. There are multiple schemas. It's all single block access. We automate all of our tests with a shell script that FlashDBA, I don't know if he's on the call, wrote, but there's a SLOB2 harness is available for automating test runs. What do they look like? So the logical IO test, again, January 18, I've run for 4 minutes or so, and on a reasonably powerful machine, and you'll see here we go, 96% of the time it is on CPU. And you'll see again, if you look at the OS Watcher output at the bottom, we've flatlined the CPU essentially at 100% usage. So you can also see, as you ramp up the number of users, what the capacity of this particular platform is when you hit 100%. One of the things we use the logical I/O test for is to derive a metric called SLOB ops per core. So a SLOB op is a single select statement, one of those SLOB select statements. And we divide the number per second by the number of cores available to the database. Why do we do that? Well, you pay for Oracle by the core, and it also enables us to compare different generations of CPUs. So one CPU might have 8 cores, and then the next generation might have 12, and be suitably more expensive. But by factoring out by the number of cores, you can say what are the most cost effective as well as the absolute best performing CPUs for your Oracle workload. And that obviously varies over time. The how, that's the SLOB conf for this test. Oh yes, and the other uses of the logical I/O test. If you're anything like me, you'll have had people make cases for alternative technology X on the basis that Oracle doesn't scale to large numbers of queries per second. Well, because logical I/O purely is a query, then it's relatively easy to say that that's a meaningless question. Let's have a look at what your queries actually are and see what your performance problem might be, but it's unlikely to be just Oracle. And here we wanted to look at what's the impact on the CPU performance of applying these OS patches. For physical I/O, we're really only interested in 2 things, the I/O requests per second and the latency at which those I/O requests happen. And there's a fairly standard sort of graph that shows as your number of IOPS goes up, so does your latency. And again, the slob.conf extract at the bottom is how do we do that test. So here's an example of an AWR report from the same machine, but running a physical I/O test. Important difference to note, the buffer cache here is 128 meg, which is about as small as we could get it without the tests crashing. So obviously with the buffer cache of only 100 meg or so and schema sizes in the gigabytes, pretty much all of your I/O is physical. And here we see 90% of our time is on user I/O. When we look at OS Watcher for physical I/O, you typically see this sort of thing, that the machine is mostly doing either waiting for physical I/O to complete. Obviously something went wrong about 1040 on this particular run. And you'll also typically see all of those system interrupts. So you'll see at high I/O levels, you'll also see the system CPU utilization creeping up as well. So we've used PIO, and you can too, to look at obviously this use case now, but also all flash arrays. What sort of service level can we guarantee? You know, can we guarantee 5,000 IOPS at 1 millisecond, or 20,000 IOPS, or 50,000 IOPS? We've used it to compare how we might present ASM devices using ASM lib or UDEV or the ASM filter driver. We've used it to stress test fiber channel drivers because we discovered that a particular fiber channel card was problematic in our service, and to evaluate fixes for bugs in the OS as well. Swingbench, I'm going to cover relatively quickly because I do want to get on to the results. As I say, SLOB is a hardware evaluation tool. So if you're looking at changing database servers, if you're looking at moving to the cloud, things like that, SLOB is an excellent tool. But if you want to communicate back to application developers, having an actual application is a great starting point. And Swingbench is a TPC-like OLTP benchmark. You can use the GUI, and it's great for understanding what's going on. You get lots of pretty graphs. I think the graphs have changed since 2018, so they're even prettier graphs now. But we always will use the CLI for our benchmark runs, and we use a standard database with the exact same parameters every time, with the same benchmark scale every time, and the same config files every time. And you run this several times, varying, you know, how long do I want to run the benchmark for? So like a burn-in test, varying the number of active users, and varying the database size, so or the database version, whatever it is that you wish to test. The measures we read out from the results file. There is now a little utility called results to PDF that's distributed with Swingbench. I've yet to look at that, but it'll save you reading XML files. Things to look at are transactions per second and the average response time, because those are the things that people are interested in. So we've used Swingbench to evaluate new patches, particularly new release updates, database upgrades in particular, impact of hardware changes. It's a very good tool for illustrating how adding rack nodes can scale your workload. It's also a good tool to illustrate how long a brownout might be in a node failover event, either using rack one node or using single instance and the CHAR functionality that's available. We also use it to demo fast application notification and application continuity to developers in an attempt to persuade them to use that feature. So some results that we got from looking at these patches. The first thing I want to say is these are not benchmark numbers that you can just take away and compare to your setup, for a number of reasons. So firstly, I've not given you full details of how we set up the benchmark, so it's not open like that. You don't know what the hardware and software versions of everything are, but I do encourage you to build your own test suites, and as I say, SLOB and Swingbench are great tools. The other thing to say is you're not allowed to publish benchmarks according to your license agreement with Oracle, and that's for good reason. So if you Google system benchmarking crimes, you'll see a long list of the way in which benchmarks can lie to you, and a long way in which you can fool yourself that you've written a good benchmark, but in fact you haven't. And I may have committed one or more of these benchmark crimes at any given point. So do adopt these tools. Don't take what I'm saying as gospel. With that all over, our CPU test, you'll see that we scale up our workload to 96 workers in the end. And the number on the y-axis is a measure of the CPU operations per second, the SLOB ops number. And you'll see that when we were fully patched, we definitely see a hit on the CPU capabilities at nearly all workload levels, certainly any non-trivial workload levels. Right up until maybe we're pushing the workload further than is really justified. I think those 96 workers were running on a 16 thread server at the time. This is the OS Watcher screen that I showed you. The screen at the top is when we had not patched the system, and then the screen at the bottom, you can see rather than being a flat line right along the zero, you can actually see that there's a measurable, albeit small, CPU impact from patching your system. And that's to be expected. We know that these patches apply when you're issuing CPU interrupts, and every application will do that. On the physical I/O side, this is our baseline. As we scale again, number of workers, we get up to about 190,000 IOPS at a very good latency. You can see we've got a very good storage array underneath the test harness, and that's a fairly typical chart. When we patch it, apart from the 122 worker level, you'll see a very similar pattern, but the thing to notice is that latencies have increased and the IOPS has decreased quite considerably. So instead of being 180 odd thousand, we're 140 something thousand IOPS. Still not shabby at all, but a noticeable impact. When we switched off, this is the flag that I said we could install the patch for and not enable the patch. We did see an increase in throughput, and the latency figures are slightly better, but they're still not back to where they were before the patches were applied. Similarly, our Swingbench benchmarks, you'll see that if everything is fully patched, there's nearly a 20% hit to the application performance. Even when we disable the KPTI patches, there is still a noticeable hit. And unsurprisingly, that shows up for end users of this hypothetical application in slower response times for each of those transaction types. Actually, yes, that is response times, not transactions per second. I've mislabeled that. I've shown you this system CPU before. We saw the same thing with the Swingbench benchmark. So what conclusions did we draw at the time? Well, there really is an impact, and we might expect a hit of up to 18% on our Oracle database servers, and a small but non-negligible increase in the I/O response time. The use of the no KPTI switch does reduce those impacts, but obviously it's somewhat problematic to apply patches and then disable them. And to reiterate, this was a very real threat for desktop machines. So you could probably be sent emails that contained exploits for Meltdown. For database servers, the case was much more arguable. From memory, what we did was that we delayed the implementation on our production systems until application teams had properly verified that the reduction in throughput didn't adversely affect their SLAs. But the key point I want you to take away, because you're unlikely to be testing Meltdown or Spectre at this point, is that both SLOB and Swingbench make very, very good platform performance tools that you can use to effectively test a large number of scenarios quite quickly. We got all of this testing done in about 3 days, because obviously we had the CTO saying, "Where's the fix?" Just as an addendum, it can also show you when vendors maybe aren't telling you the truth. So this was some generations, I'm not going to name the vendor, but going from generation 1 to generation 2, we saw a very big increase in comparative CPU performance in terms of SLOB ops per core. When we then looked at the generation 3 servers, we saw a very, very small increase. And in fact, we continued using the generation 2 servers for about another 1.5 years because the cost per CPU wasn't worth the small increase in performance. So that sort of thing is really quite handy to have in your back pocket. Right, that's the presentation. I can see one Q&A from Quamwen. The relationship between SLOB and VO. So the question is, what is the relationship between SLOB and PIO? That's a good question. So SLOB is an IO benchmarking utility that Kevin wrote and can be used to measure a number of different IO performance characteristics. PIO is, I'm using as an acronym for physical IO. So that's the SLOB test that you run essentially with the smallest buffer cache you possibly can, so that all of your IOs result in actual physical IOs. In contrast to the logical IO test, where you also run SLOB, but you expect to answer all of your selects from memory. So it's purely a CPU measure. Does that answer the question? Excellent. Okay, I don't have any other questions.
At the moment, we don't have any other questions. I see a raised hand. People raising hands, please use the Q&A one so we can read out the questions aloud to everybody. We still have a couple of minutes time before the break for the next talk. So please feel free to type anything you still want to ask of Neil into the Q&A window. Otherwise, if no new questions are coming, I would say thank you, Neil, for the moment. Very nice presentation, very in-depth, loved it. If you could just stay on until